Hello, my dear students. Welcome back to MKG Online Study, an e-learning platform. Imagine this. It's 1973. A man in a suit is standing on a street corner in Midtown Manhattan. He pulls out a device. It's about the size of a brick, weighs nearly a kilogram, and has a massive antenna sticking out of the top. People walking past are staring at him like he has lost his mind. And then he makes a phone call. That man was Martin Cooper, an engineer at Motorola. And that was the world's first ever mobile phone call. The call lasted just 30 seconds. The battery, it lasted 20 minutes. The phone itself cost the equivalent of about $10,000 in today's money. Now fast forward to today. You are watching this video possibly on your smartphone while sitting in a moving vehicle or lying in the bed or maybe even while eating lunch. You are streaming HD video wirelessly in real time without even thinking about it. You don't even think of it as amazing anymore. So, how, in just 50 years, did we go from a $10,000 brick that makes 30-second calls to a device in every pocket that streams Netflix, navigates cities, processes payments, and connects billions of people instantly? This is exactly what this lecture is about. So, this lecture is our complete mobile computing series designed specially for your university students. Today, we are going to trace the entire history and evolution of mobile communication from the very beginning all the way to 5G and beyond. Now I want to make you a promise about this lecture. By the time we are done today, you will not just have memorized facts for your exam, you will actually understand this topic. You will be able to explain it to someone else. And that is how you score full marks, not by remembering words, but by understanding ideas. So let's get into it. Keep a notebook ready because there is a gold in here for your exams. Before we dive in, let me tell you exactly what you are going to be able to do by the end of this video. These are your learning objectives, and I want you to read them and actually think about each one. First, you will be able to explain the pre-cellular area. What was communication like before mobile phone existed? Why were those systems so limited? This is actually a question that many students skip in exam, and it's easy marks if you know it. Second, you will be able to trace the evolution from 1G all the way to 5G with the key features, technologies, and real world impact of each generation. This is the core of today's lecture. Third, you will be able to recall the important years, standards, and technologies. JSON, CDMA, LTE. These terms will mean something to you after today, not just sound like random letters. Fourth, this is crucial for exam. You will be able to draw and complete the generation comparison table. I will tell you right now, this table appears in almost every mobile computing exam paper. After fifth, we will be discuss future of mobile communication, 6G, satellite internet, AI-driven networks, smart cities, what's coming next, and why it matters. Alright, 5 objectives. Let's go through one by one. The pre-cellular area, 0G area. Let's start at the beginning. Before mobile phones, before cellular network, before any of the technology we take for granted today. We call this era 0G, zero generation. And the reason it is called zero is because it wasn't really a mobile phone system at all. It was more of radio communication system that happened to be mobile. So what was 0G? Before mobile networks existed, wireless communication used something called push to talk system or PTT system. You have definitely seen this before, even if you didn't know the technical name. Think of walkie-talkies. Think of the radio on a police officer's shoulder. Think of those construction site radios where someone says, copy that over. That's push to talk. That's 0G. These systems were used mainly by the military, police, emergency services, and taxi dispatchers. They were large, heavy, needed their own radio towers, and were absolutely nothing like what we consider mobile communication today. How did it actually work? Here is the key technical concept. 0G used half-duplex communication. Now write this down because it comes up in exam. Half-duplex means one person can speak at a time. You press a button to talk, you release the button to listen. You cannot do simultaneously. There is no real way conversion happening at the same time. Compare this to a normal phone call today, where you and I can speak at the same time, interrupt each other, and it works perfectly. That is called full duplex, two-way simultaneous communication. Zero's G was half duplex, one way at a time, like a one-lane road where one car can pass at a time. Think about how frustrating that must have been. Imagine trying to have a business meeting like that or calling your family in an emergency and having to wait for them to finish speaking before you could say something. What were the key systems in 0G era? There were the three main ones that you should know for exam. First, MTS, the mobile telephone system, launched in 1946 in the United States. This was actually the first commercial phone service, but it required a human operator to manually connect your call. You couldn't dial someone directly. You had to call an operator, tell them who you wanted to reach, and they would patch the connection. Imagine that. Second, IMTS, improved MTS, which came in 1960s. This improved things slightly. You could now dial directly without an operator, but it was still half duplex, still very limited in coverage and very expensive. Third, AMPS, precursor system in the 1970s. These were the building blocks that could eventually become the first true cellular network. Now the most important, the limitation of 0G. And I want you to write this down because this is very common short answer exam question. What are the limitations of pre-cellular mobile communication? No privacy. Anyone with the right radio receiver could tune into your conversation and listen. Every conversation was essentially public. There was no encryption, no security. If you said something sensitive on a 0G call, anyone could hear it. Second, only one call per frequency. Each radio frequency could only carry one conversation at a time. If someone was using a frequency in your area, you had to wait. This made the system incredibly inefficient. Limitation 3. No roaming between cities. You were tied to a specific geographic area. If you drove from one city to another, your system won't work. There was no handover, no continuity of services. You could Your call would simply drop. Limitation for huge heavy equipment. There were no portable devices. They were installed in vehicles, cars, trucks, police vehicles because they were far too large and heavy to carry. The idea of putting one in your pocket was laughable. Limitation 5. Manual operator switching. In many systems, a human had to physically connect your call. This meant delays, limited hours of service, and no calls when the operator was unavailable. Limitation 6. Very limited coverage area. The radio towers had small range and there were very few of them. Coverage was only in major cities, and even then it was patchy. So, to summarize, 0G push to talk, half duplex, no privacy, no roaming, manual switching, massive equipment, very limited coverage. These limitations are exactly what the engineers of the 70s and 80s set out to solve, and that brings us to 1G. Welcome to 1980s. Big hair, neon color, and the world's first true mobile phone network. 1G, first generation, is where the mobile revolution truly begins. The big moment, 1979. That year, Japan's entity, Nippon Telegraph and Telephone, launched the world's first commercial cellular mobile network. This was a massive technological achievement. For the first time, you had a proper network of towers, proper handover between areas, and a system designed specially for mobile phones, not military radio. 4 years later, in 1983, the United States launched AMPS, the Advanced Mobile Phone System, in Chicago. This became the dominant 1G standard in America. So, for example, Japan was first in 1979, US launched AMPS in 1983. What technology did 1G use? 1G was an analog network. The sound of your voice can convert it into an analog electrical signal and transmit it over radio waves. There was no digital conversion, no compression, no data encoding. The access technology was called FDMA, Frequency Division Multiple Access. This is another important term. FDMA means the available radio spectrum is divided into separate frequency bands and each user gets their own frequency channel for the duration of a call. It's like dividing a highway into lanes. Each car gets its own lane and says in it. Write down this. 1G equals to analog plus FDMA. What about voice quality? Poor, very poor by today's standard. Call had static, interference, and crackling. If you were ever heard an old radio with poor reception, that's what 1G voice quality sounded like. And because the signal was analog, it was extremely easy to intercept. Anyone with a radio scanner could listen to your calls. There were stories of journalists and curious hobbyists listening to celebrity phone calls in 1980s because 1G had zero encryption. Your conversation was transmitted as a raw analog signal, no security whatsoever. Data services on 1G, none, absolutely zero. You could make voice call, that's it. There was no SMS, no internet, no data of any kind. Mobile communication in 1G era meant one thing only, talking. The 1G handsets, the brick. Let's talk about the actual phones of this era. The most famous was the Motorola DynaTAC 8000X released in 1984. This was the phone that Cooper had made that historic call on. Let me give you the specs. Weight 790 gram, almost a kilogram. Your phone today is probably around 180 to 200 grams. Height 33 centimeters. That about the length of a ruler. Battery life 30 minutes of talking time, then 10 hours to recharge. Price $3,995 in 1984. That's about $20,000 to 13,000 in today's money. That is why it was nicknamed the brick. And despite all of that, the weight, the size, the cost, it was a status symbol. Wealthy business people carried them as a sign of success because even with all those limitations, the ability to make a phone call without being near a landline was genuinely revolutionary. The limitation of 1G compared to what came after 1G had a serious problem. Voice quality was poor and inconsistent. No security or encryption calls could be intercepted easily. No data services, voice only. Roaming between countries was essentially impossible. The devices were bulky and expensive. Limited capacity, not many people could use the network simultaneously. These limitations made it clear analog wasn't going to cut it for the future. The world needed something digital. Exam formula for 1G. Analog plus FDMA plus voice only plus no security. Plus first commercial network. Japan 1979 plus eMBS USA 1983 plus Motorola DynaTAC. Let's move to second generation. Now we come to the one of the most important transition in the history of mobile communication, the shift from 1G to 2G, from analog to digital. This changed everything. The bit shift analog to digital. In 1G, your voice was transmitted as a continuous analog wave, like water flowing through a pipe. Any interference in that pipe, noise, other signals, physical obstacles would distort your voice. In 2G, your voice was first converted into digital data, a sequence of zeros and ones, and then transmitted. Digital signals are far more resistant to interference. They can be compressed, encrypted, and error corrected. The quality improvement was dramatic. Think of it like the difference between a cassette tape and a CD. The cassette degrades, wraps, gets frizzy over time. The CD gives you the same clear digital audio every time. That's roughly the difference between analog 1G and digital 2G. 2G was officially launched in Finland 1991 and the standard was called GSM, the Global System for Mobile Communication. GSM, the standard that conquered the world. GSM became the dominant mobile standard globally. Let me tell you what made it so important. First, it was truly global. By agreeing on one standard, different countries' network could communicate with each other. This made international roaming possible for the first time. Second, it used TDMA, time division multiple access, as it access technology. Unlike FDMA, which gave each user their own frequency, TDMA divides each frequency channel into time slots. Multiple users share the same frequency, but each user gets their own time slot, like turns in a conversion much more efficient. Third, GSM introduced the SIM card, subscriber identity module. This was genuinely revolutionary. Your identity, your mobile phone, your contacts all stored on a small chip that you could take out and put into any phone. Before SIM card, you were tied to a specific device. With SIM card. The card became your identity, not the phone. What was new in 2G? The key innovation. The most exciting things that 2G introduces was SMS, short message service, the ability to send text. Here is an amazing fact. The very first SMS ever sent was on December 3rd, 1992 by a software engineer named Neil Papworth to his colleague Richard Jarvis. The message, Merry Christmas. Nobody expected SMS to become what it did. The engineer who designed GSM thought of SMS as a small bonus feature. Within a few years, people were sending billions of messages per day. SMS became arguably the most popular form of communication in human history. At that point, an entire culture developed around it. Abbreviation like LOL, BRB, OMG, all born from SMS because message had 160 character limit. Beyond SMS, 2G also offered basic data service, very basic. We are talking about 9.6 kilobits per second. To put in perspective, a single photo you take it today is maybe 3 to 5 megabytes. At 9.6 kbps, downloading that one photo would take about 40 minutes. So data was technically there, but practically very limited. Security also improved dramatically. 2G used digital encryption, making it much harder to intercept calls compared to analog 1G. 2G variant, the 2.5G and 2.75G era. As technology improved, 2G got upgraded. GPRS, General Packet Radio Services. This was 2.5G, launched around 1998. to 2000, speed improved to up to 114 kbps. This allowed basic web browsing on mobile phones for the first time, though it was painfully slow by today's standard. Edge, enhanced data rates for GSM evolution. This was 2.75G. Speed improved further to up to 384 kbps. This is when mobile internet started becoming actually usable. The alternative, CDMA. While most of the world adopted GSM, the United States has also used a standard called CDMA, Code Division Multiple Access IS-95. Instead of dividing by frequency or time, CDMA gives each user a unique code, and all users transit simultaneously on the same frequency using their codes to separate conversation. Qualcomm developed this technology and it was used by carriers like Verizon, Spirit in the USA. CDMA versus GSM was a big debate in the 90s and early 2000s. But GSM unlimitedly won globally. Japan had its own standard called Personal Digital Cellular PDC, and the US had a DAMPS, digital AMPS, but globally GSM dominated. 2G was the Nokia era. The Nokia 3310, the Nokia 5110, these were the phones of the late 90s and early 2000s, and they were everywhere. Simple, reliable, long battery life, and virtually indestructible. The Nokia 3310, ma'am, about surviving everything. That's real legacy. Exam formula for 2G, digital plus GSMA plus TDMA plus SMS introduced 1992 plus SIM card plus GPRS 2.5G plus Edge 2.75G plus launch Finland 1991. Now let's move to third generation mobile. We are now entering the 2000s and the world is changing fast. The internet has exploded. Everyone has email. Everyone is browsing the web on their computers. And people are starting to ask a very reasonable question. Why can't I do this on my phone? 3G was the answer, the big promise of 3G mobile internet. The defining feature of 3G is that it has brought the internet to mobile phones. Probably not the painfully slow web browsing of 2G, but actual usable internet. The technology behind 3G is called WCDMA, that is wideband code division multiple access, which uses a wider band of radio spectrum and is far more efficient than 2G technologies. There were an alternative standard in the US called CDMA 2000, developed by Qualcomm. Both of these fell under the international framework called IMT 2000, International Mobile Telecommunication 2000. This was the ITU's, International Telecommunication Union's, specification for what 3G should achieve. When did 3G launch? The first commercial 3G network was launched by NTT DOCOMO in Japan in 2001. Japan was again first, just as they were in with 1 GB. In Europe, UMTS networks, Universal Mobile Telecommunications System, the 3G standard there launched in 2003. The speed jump, moving from 2G to 3G, was enormous in terms of speed. 2G Edge 2.7, 5G 384 kbps maximum, 3G WCDMA up to 384 kbps while moving and up to 2 Mbps while stationary. 2 megabits per second, that might not sound impressive per today's standard, but compared to 2G data speed, it was transformational. You could now actually browse websites, check emails with attachment, download, type, and also consume real internet contents on your phones. Later, HSPA high-speed packet access was introduced as an upgrade to 3G, pushing speed even higher. This became known as 3.5G. What 3G made possible? This is where it gets exciting. Video calls. 3G was the first generation to support actual video calling from a mobile device. You could see the person you are talking to. This was science fiction just a few years earlier. Email on mobile, checking your inbox, reading, sending emails with attachment, all from your phones. Mobile web browsing, not WAP pages, but actual websites, though they loaded slowly and weren't optimized for mobile yet. App download. The early days of downloading games and small apps to your phones. And most importantly, 3G enabled the smartphone revolution. Think about this, the iPhone launched in 2007, Android launched in 2008, the App Store launched in 2008. None of this could have been possible without 3G mobile internet. You can't have a smartphone if there is no data connection fast enough to do anything meaningful with it. Steve Jobs specially said that 3G connectivity was one of the enabling technologies for the iPhone. The entire ecosystem we know today, App Store, social media on phones, mobile banking, Uber, WhatsApp, all of it traces back to 3G making mobile internet real. The limitation of 3G. Even with all its advances, 3G had limitations. 2 Mbps was still too slow for video streaming. Latency was high, around 100 to 200 milliseconds, making real-time applications difficult. Coverage was patchy in rural and developing areas. Battery drain was significant on early 3G devices. These limitations set the stage for what came next. Exam point of view, WCDMA oblique CDMA 2000 plus IMT 2000 standard plus 2 Mbps peak speed plus mobile internet plus video calls plus enabled smartphones plus launched Japan 2001, entity DOCOMO plus Europe UMTS 2003 plus HSPA upgrade to 3.5G. This is our third generation. Now, next move to fourth generation mobile 4G. By the late 2000s, the world had smartphone. The iPhone had launched. Android was growing rapidly. People were carrying pocket computers everywhere, and now they needed those pocket computers to actually be fast. 3G mobile internet was real, but it wasn't fast enough. Video streaming would buffer, large file downloads took forever, gaming was laggy, the world needed more, much more. Enter 4G, fourth generation, the network that truly made the smartphone era possible. The numbers. Let's start with the headline number because they were impressive. 100 Mbps peak download speed while mobile. 1 Gbps peak speed while stationary. Less than 50 millisecond latency versus your 3G that is 200 milliseconds, which is very less. To appreciate what 100 Mbps means on your 3G, you could download a 10 MB song in about 40 seconds. On 4G, you download it in less than a second. You can stream a full HD movie. You can video call in a high definition without it freezing. Everything that felt slow on 3G become instant on 4G. The standard LTE 4G official standard is called LTE long term evaluation. You see on your phone all the time the little LTE indicator in the top corner. The technology behind LTE is OFDMA, orthogonal frequency division multiple access on the downlink, and FDMA on the uplink. Downlink means data coming to your phone. Uplink means data going from your phone to the tower. OFDM is much more spectrally efficient than previous technologies. It splits the signal into many small subcarriers and transmits them simultaneously, which dramatically increase speed and reliability. There was also an advanced version called LTE Advanced, which could theoretically reach even higher speed. When did 4G launch? The first 4G LTE network was commercially launched in December 2009 by TeliSonera in Sweden and Norway. Then it rapidly spread worldwide through the early 2010. India's 4G story is particularly dramatic. Reliance Jio launched in September 2016 with free 4G data, completely disrupting the Indian telecom market and triggering massive 4G adoption across the country in just a few years. The all IP revolution. One of the most technical significant things about 4G is something that often gets overlooked. It was the world's first all IP network architecture. What does that mean? In earlier generation, mobile networks were a hybrid of circuit switching for calls and packet switching for data. Circuit switching means a dedicated connection is established for the duration of a call like a private phone line just for you. It's a reliable but inefficient. 4G eliminated circuit switching entirely. Everything calls, data, video travels as a IP packet. This is the same technology that powers the internet. The result is much more efficient, flexible, and scalable network. What 4G enabled? The app economy. This is where we have to stop, appreciate just how much 4G changed everyday life. It wasn't just faster internet, it enabled entirely new industry and ways of living. YouTube and video streaming. HD video in your pocket anywhere, anytime. Before 4G, YouTube on mobile was a buffering nightmare. Netflix on mobile, high quality video streaming being became possible only with 4G speed. Instagram. Think about Instagram requires high resolution photos and videos. Upload and download constantly with real time feeds. That's a 4G experience. Uber and Ola, real-time GPS tracking, location sharing, payment processing, all happening simultaneously on your phone. WhatsApp voice call and video call, VoIP, voice over internet protocol. Calls became crystal clear on 4G, challenging traditional telecom. Mobile gaming. Exam formula for 4G, EDGE plus OFDMA plus SG, FDMA plus 100 Mbps plus 1 Gbps stationary less than 500 millisecond latency plus all IP architecture plus launch Sonera. Sweden, Orbit, Norway, December 2009 plus enable streaming Uber, Instagram. Now we move on to our fifth generation, the current revolution, and we are at the present, the generation we are living in right now, fifth generation. 5G started commercially development in South Korea in April 2019, making South Korea the first country in the world to have a nationwide 5G network. Other major markets followed quickly: US, China, UK, Japan, Australia, and increasingly India. The speed: 5G headline number in 10 Gbps. That's 10 gigabits per second peak theoretically speed. Let me put in perspective: 4G gives you 100 Mbps, 5G gives you 10,000 Mbps, that is 100 times faster than 4G. At 10 Gbps, you could download a full HD movie in under 2 seconds. You could download an entire season of a TV show in about 30 seconds. You could download 100 songs in less than a second. But speed alone is not what makes 5G truly revolutionary. What makes 5G different is what it enables. And for what we need to understand it. Three use cases. The first use case is 5G was designed with three fundamentally different types of application in mind. Not just fast internet, three specific use cases are eMBB, Enhanced Mobile Broadband. eMBB is about giving existing mobile internet user a dramatically better experience, faster speed, more capacity, better coverage. What does eMBB enable? 4K and 8K video streaming on mobile, crystal clear, zero buffering. Augmented reality and virtual reality, AR/VR. Experiences require massive bandwidth and very low latency to work without making you feel sick. 5G eMBB makes this possible. Cloud gaming, playing graphically intensive games streamed from the cloud like Google, Stadia, or Xbox cloud gaming. That's urban connectivity. In a football stadium with 80,000 people all on their phones, 4G collapse. 5G eMBB handle it. Next, case 2, URLLC, ultra reliable low latency communication. This is game changing use case, the one that could literally save lives. URLLC provides latency of just 1 millisecond, 1000 of a second compared to that of 4G's 50 millisecond and 3G's 200 millisecond. This near zero delay is required for application where any lag could catastrophic. What does URLLC enables? Autonomous vehicle. A self-driving car needs to make decision in milliseconds. If the car signal to a network has a 50 millisecond lag, there is suddenly a child in the road. That 50 millisecond could mean a collision. 1 millisecond URLLC makes autonomous vehicles safe. Remote surgery. A surgeon in Mumbai could operate on a patient in a rural village using a robotic arm with the robot controlled over a 5G URLLC connection. 1 millisecond latency means the surgeon had movement are replicated almost instantly. With 50 millisecond delay, this would be too risky. This is real. Trials are already happening. Industrial automation, factory robots, precision manufacturing, real-time processes, control, all requiring ultra reliable, ultra low latency communication. Smart power grids monitoring and controlling electricity distribution in real time. mMTC, massive machine type communication. mMTC is about connecting not people but machines, billions and billions of machines. 5G mMTC can support 1 million connected devices per square kilometer. Think about what that means. In a smart city, every traffic light, every road sensor, every air quality monitor, every dustbin, every parking space, every street light, all connected, all communicating all the time. What does mMTC mean? Enable Internet of Things, IoT, at massive scale. Your smartphone is a tiny preview of mMTC. Imagine entire city working like that. At smart agriculture, supply chain tracking, smart healthcare, patient monitoring, medical equipment tracking, hospital management. Key technologies behind 5G. Millimeter waves, waves, massive MIMO. MIMO stands for multiple input, multiple output. Beamforming, instead of broadcasting signal in all directions like a traditional antenna, beamforming focuses the signal like a beam of light directly at a specific device. Much more efficient, much more stronger signal. Network slicing. 5G can create multiple virtual network on same physical infrastructure. An ambulance gets a dedicated high priority slice with URLLC quality. A Netflix user gets an eMBB slice and IoT sensor gets an mMTC slice all on same network. Exam formula. For 5G, three use cases eMBB plus URLLC plus mMTC plus 10 Gbps plus 1 millisecond latency plus 1 million devices per kilometer plus 1 wave plus massive MIMO plus beamforming plus network slicing plus launched South Korea April 2019. Next is generation comparison, the exam table. This slide I told you about at the beginning, the slide that could be worth 5 to 10 marks in your exam. I want you to pause the video right now, get your notebook, draw a table with 5 columns, generation, era, technology, speed, and key feature. Then unpause and write with me. Ready? Let's go through it row by row. 1G era 1980s technology, FDMA, analog speed. Speed 2.4 Kbps, key feature, half duplex, no privacy, push to talk. 1G era 1980s technology, FDMA analog, speed 2.4 Kbps, key feature, voice only, no security, AMPS standard. 2G era 1990s technology, TDMA, GSM, CDMA. Speed 64 to 384 kbps. Key feature digital voice, SMS, SIM card, GPRS EDGE. Next generation is third generation ERA 2000 technology. WCDMA, CDMA 2000, speed 2 Mbps. Key feature mobile internet, video calls, smartphone. 4G 2010 era technology LTE OFDMA DMA speed 100 Mbps. Key features HD streaming all IP ultra low latency. 5G era 2019 onwards technology Wave massive MIMO speed 10 Gbps. Key feature IoT at scale. Three use cases eMBB, URLLC, mMTC, autonomous vehicle, smart cities. Got all that? Good. Now here is my exam tip. When you write this table in exam, add a brief one-line explanation after the table. Something like each generation has brought approximately 10x improvement in speed and introduced entirely new categories for services from voice only in 1G to massive IoT connectivity in 5G. That one sentence shows the examiner that you understand the big picture, not just the individual facts, that difference between a B and A. Future beyond 5G and 6G. 5G is still being developed across the world, but researchers, engineers aren't waiting. They are already working on what comes next. 6G expected around 2030. 6G reach is already underway at major companies Samsung, Nokia, Ericsson, and at university and government labs around the world. Targets 1 terabit per second peak speed, that's 100 times faster than 5G's 10 Mbps. Sub-millisecond latency even lower than 5G 1 millisecond. Full integration of AI at the network level. The network itself will think, adapt and optimize in real time. 6G will likely even higher frequency called terahertz waves and will require a fundamentally new approach to network architecture. The ITU, International Telecommunication Union, is already working on the 5G standard, officially called IMT 2030. This is already happening right now. Satellite internet, Starlink. Elon Musk's SpaceX project has launched thousands of small satellites into low Earth orbit. OneWeb is another similar project. Key innovation here is the LEO low Earth orbit satellite instead of traditional geostationary satellite. AI-driven network. The network of the future will be largely self-managing. AI algorithm will continuously monitor network conditions, traffic patterns, interference, device location, and automatically adjust bandwidth allocation, routing, and coverage. Instead of engineer manually configuring network settings, AI will handle it in real time. This is called autonomous networking or self-organizing networks. The result is more efficient, more reliable, more responsive network with less human intervention needed. Smart cities and IoT. 5G and 6G together will enable what many people call the fourth industrial revolution, a world where the physical and digital are deeply integrated. In a smart city, traffic light talk to cars, road report their own conditions, energy grids balance load automatically, emergency services respond faster because sensors throughout the city feed real-time information. Hospital monitor patients remotely, water system detect leaky instantly. The mobile communication that started a 30-second phone call in 1973 is evolving into a nervous system of our entire civilization. All right, everyone, let's bring it all together. We started with 0G, the pre-cellular era, push to talk, half-duplex, walkie-talkie, and radio dispatch. No privacy, no roaming, manual operator, limited range. Then came 1G in 1980s, the first real mobile phone network, analog technology, FDMA, voice only, no security, eMBP in the US and legendary Motorola DynaTAC, the brick. Then 2G in the 1990s, the digital revolution, GSM, TDMA, SMS, introduced in 1992, SIM cards, GPRS, and the Edge for basic data. The Nokia era, mobile phones become a mass consumer product. Then 3G in the 2000s, mobile internet arrived. WCDMA, 2 Mbps, voice calls, the iPhone, the App Store, the smartphone era was born. Then 4G in the 2010s, speed, LTE, OFDMA, 100 Mbps, all IP, Netflix, Instagram, Uber, WhatsApp, mobile internet become an actual as breathing. And now 5G, 10 Mbps, 1 millisecond latency, 3 use cases, eMBB, URLLC, mMTC, powering IoT, autonomous vehicle, remote surgery, and smart cities. And beyond 6G by 2030. Satellite internet, AI-driven networks, a fully connected world. That's the story of mobile communication from walkie-talkie to smart city, from 30-second call to 1 terabyte per second downloads in just 80 years. Before you go, three things I want you to do. One, review the comparison table you wrote. Make sure all six generations are there with their technology, speeds, and key features. Two, in the comment below, tell me which generation do you think had the biggest impact on everyday life. I read every comment. I had love to know what you think. Three, subscribe and hit the bell icon so you get notified the moment next lecture drops. In the next lecture, we cover the characteristics of mobile computing. That's also a guaranteed exam topic. If this lecture helped you, please give it a thumbs up. It takes 2 seconds and it genuinely helps this channel reach more students who need this content. I see you next lecture. Thank you. Thank you.